Okay. Good afternoon. Is anyone here a physicist or an expert in quantum computers? All right, cool. So hopefully I won't get heckled too much. So my name's Tess Schrodinger. I'm a security engineer with Digital Cloak LLC. I'm not sure if you have to legally say that part or not. The first thing I like to do is explain how this talk came to be. So for those of you who don't know me or who haven't heard me speak before, probably 5-6 years ago, I knew little to nothing about IT. The most complicated thing I could do was put my out-of-office email on, maybe put a picture in my signature. That was pretty cool for me. In the process of getting my master's degree in security management, I had noticed there were all these options to take IT security classes. And I confess, I was like, oh, that's hard. I'm a girl. I can't, So I was like, I'm not going to go near any of that stuff. I'm just going to there's smart people out there doing that. I'm going to let them keep that their thing. So I thought I was being pretty clever and completely avoiding all this cybersecurity and just staying with like locks and doors and bodies and stuff. And then I sat down with my advisor for my capstone to get ready to take the big final thing for your master's, and he informed me, this is how it works. We're going to have you take you get 4 questions. You have to write a paper on each question. This is in a closed room, no notes, no nothing. It's just completely from your head. They can be on anything. And I said, well, you're going to look at my classes I took, and you're going to pull questions from that, right? And he goes, oh, no. No, if we give you a master's in security management, you better be a master. So if there's any areas you might have, not covered real well, you might want to catch up on those. So this prompted a hysterical dash down the hallway to my then boss's or my mentor's office, to which I said, oh my God, you have to make me a master of IT security in 6 months. And he said, not a problem. And suddenly here I am. So in the course of this, pounding all this stuff into my head over 6 months, and I'm actually proud to say that 2 of the questions when I sat down that day were on cybersecurity, and they were the 2 questions I scored the highest on for the papers. So I think I did really well. But the thing that really captured me during all this learning was how integral IT is to regular security. And a lot of standard security folks don't realize that. They still think, like I did at the time, that's something those smart people do with the machines and, the hacking and all that. And through all the studying I did, it really became so clear to me how integral. It's all just coming together now. There's no way you can be just one or the other. You've really got to kind of know both of them as we go into the future. But during the course of all this studying, I got so interested in it, I actually, once I got the regular master's, I went for the master's in cybersecurity technology from UMUC, because now I wanted to really get into it. I didn't want to just cram because I needed to just on the side. I really got fascinated with it, so I wanted to learn more, and I wanted to get better, and I actually wanted to start getting my hands on things. And during the course of that graduate work, I started running into all these comments here and there on, when quantum computers become viable, encryption as we know it is going to go out the window. It's going to be destroyed. Nothing will be secure ever again. Oh my God, the sky is falling. And I wanted to know why. So, of course, I went to my mentor and I said, hey, why? And he looked at me and he said, I have no clue. Which that kind of stunned me for a moment, because he's probably the smartest man I know, and I thought he knew everything, and he didn't. So then I went to another friend that, was in IT, and I said, but why? And he just looked at me and said, beats the shit out of me, I don't know. And I'm going, oh, wait a minute. So then I started going to these cons, right? DEF CON, these really smart people at IT, surely they would be talking about this. And I'd go through the schedules and I'd look for, and there'd be nothing. So what do you do when you're a hacker and you don't know how something works? And there's nobody there to tell you. Well, you figure it out yourself. So what this talk is me basically going, why, and nobody out there could tell me why, so I had to figure it out myself. And to kind of justify the 3 o'clock 3 o'clock in the morning reading and, you know, all the work I was doing, I thought, well, maybe I should talk about this so I don't feel like the most enormous geek on the planet just trying to figure out why for myself. So I kind of told myself I was doing this for all you guys too. So that's kind of how I justify some of that. So the agenda, we're going to go over some classical physics versus quantum physics. I really make a huge attempt to keep this talk at a level that everyone can understand. My 10-year-old daughter has sat through it and she got it. So hopefully you guys will get it too. We'll go, once we get some common vocabulary via that, we'll do some classical computers versus quantum computers. And then we'll do a little bit of quantum key cryptography, some quantum hacking. For those who don't realize it, you're about 10 years late to the party. They've been quantum hacking for quite some time now, believe it or not. So I'll go over a little bit of that. And then, of course, anyone who's done a significant amount of grad work knows you have to have a proper conclusion for everything. So we'll have one of those. So a little bit more about myself. I started out in forensics. I tell people I was bullets and blood, not ones and zeros. So back when I was wearing a badge and carrying a gun, we didn't really ever encounter computers or IT at all. And if we rarely stumbled upon one at a crime scene. I'm kind of really old, so not everybody had computers in their houses then. So we didn't really run into that a lot. So my background is primarily in law enforcement, security, counterintelligence, and regular bullets and blood forensics. And within the last 5-6 years, I've made the shift over. My mentor then, my new boss now, welcomed me with open arms and has given me my first big girl IT for real job. So I'm real proud of that. And I have an undergrad I have associates in physics. I have a BA in sociology, because that's really important to kind of know how people think and how groups of people think. My master's is in security management, and of course I have the grad cert from UMUC in cybersecurity technology. I do have one little cert, my Security Plus. If you do any work in DC, you kind of have to have one of those. And I'm kind of looking at, like, what am I going to do next? So let's start with some classical physics versus quantum physics. This is where I ask you to take the red pill, okay? For those of you who are not familiar at all with quantum mechanics, Niels Bohr is a famous physicist, and he once said, if quantum mechanics hasn't profoundly shocked you, then you don't understand it yet. It can get a little squirrely, and it kind of requires you to kind of think a lot differently than maybe you're used to thinking. So just kind of relax a little, you know, let the brain go, put your feet up if you need to. And we'll try and make this painless. Newtonian physics is probably what most of you all learned in school, okay? This is trajectory-based physics, okay? So if you have a particle, right, or an object or an item, and you know the position x at some given time t, and then you know any factors affecting its just gravity or wind shear, or, you know, the temperature, etc., you can pretty much know where that particle is going to be in its trajectory. Okay? Would anyone like a particle? Anyone? So you can see the trajectory of that particle. Anyone else? Okay? So at any time, I can calculate where that particle has been, where that particle is, or where it will be. And I can give you all that information for it as it goes through that trajectory. And so think of classical physics that way. This is a picture of an electron or an atom that you're probably familiar with from school. I'm like getting old enough now that I don't know what some of you younger kids saw in your textbooks. But this model of an atom is about 70 years out of date. Okay, so if this is what you grew up knowing as an atom, this isn't very accurate. Why? Well, when physicists went and took classical physics and applied it to this model of an atom, it collapsed in on itself in like nths of a second. Well, we know that doesn't happen. So something else had to be going on here, okay? Does this mean we throw classical physics out the window? No, no, because classical physics is only flawed when you're dealing with things that are at a very, very tiny subatomic level, and that's when quantum mechanics is going to take over, or when you're dealing with things that are approaching the speed of light, and that's when your relativity theory is going to take over. For stuff in between, classical physics is sufficient, and it's also a lot easier to use that math than the relativity or the quantum stuff. So it's sufficient if you want to know ballistics at a crime scene or a basketball trajectory or, you know, the egg drop from class in high school. But once you get into those specialized areas, the subatomic or the speed of light, you're going to have to go into a different set of math. And that's going to take us into the quantum physics. Okay. One of the neat ways I heard it described by a quantum chemistry teacher was, in classical physics, if I drop this ball on the table, let's hope I can catch this and not look like an idiot. Okay, we can calculate the drop, the gravity, we know it's going to hit this, we can calculate it coming, we can calculate all this, because in classical physics, every time I drop this ball, it's going to go straight down, depending on, you know, if a giant gust of wind comes, that could change things. It's going to go straight down, it's going to hit that table, and it's going to come straight back up, right? In quantum physics, I can drop this ball, and it might hit the table. It might end up in that corner. It just might blink out of existence and end up over there. It could come all the way to here, vanish, reappear, and appear to go straight through the table, but not. It's no longer here, and suddenly it's here. So things are going to get a little weird when you get into the subatomic level, because instead of dealing with trajectories, you're now dealing with probabilities. Now, this is a more current model of an atom, okay? They were able to look at protons and neutrons, and they determined that they actually had a substructure. Okay, the electron at this time is still considered an elementary particle, meaning it does not have a known substructure, or they're pretty confident it doesn't have one. Things can always change tomorrow, though, in physics. But with the proton and neutron, they determined there was a substructure of things called quarks. Okay, those are smaller particles that make up the proton and the neutron. These are your quarks. Actually, I just think these are adorable. But this was neat because it kind of described the relationships between them. You have up, down, top, bottom, charmed, and strange. Up and down are going to be, they have the lowest mass, and they're the most common. They're the ones you're going to find in your everyday items like Twinkies and chairs and, you know, gray hairdos. The other ones, the charmed bottom, or the charmed, strange, those are found in more like high energy sort of environments like cosmic rays or particle accelerator at CERN. That's where you're going to find those types of quarks. Now, there were 4 key experiments in classical physics that kind of brought about like the downfall, I guess you could say. The first one's Planck's UV catastrophe. Now, so there's an interesting trivia. I love trivia. Catastrophe doesn't always mean a disaster, okay? Abrupt changes in direction or velocity on a graph or a chart are called catastrophic points in math. So there's actually an entire field of math that deals with this called catastrophe theory. So Max Planck was a German theoretical physicist, and I'm going to throw some years out there so you can realize this just hasn't happened recently. This is going on in 1918. He won the Nobel Prize for putting forth quantum theory. And the catastrophe was that, you know how when you heat something up, the color changes? And it goes kind of from yellow to red to white. Well, as you heat something up, you see more wavelengths being emitted. So that's why when you get to the white, you see like all the wavelengths and you're getting that really high temperature. And then as it cools down, again, you see the reverse happen, right? So some scientists said, this will be cool because we could probably predict this on a curve, on a graph, right? Well, they sat down to do that, and it worked really great until suddenly it didn't. Suddenly, like the whole thing fell apart, and that's what they call the UV catastrophe, was when this graph just suddenly out the window. Something happened, and something else is going on again at this subatomic level. So this was when Planck had to figure out what was going on, and he came up with some equations that stated radiation comes in little tiny packets, which he called photons. All right, Star Trek fans will be forever grateful now. So Einstein used this photon equation set of Planck to describe the photoelectric effect. Are you guys familiar with that? This was, actually a lot of people think he won the Nobel Prize for his theory of relativity, but he actually won it for this, the photoelectric effect. And this is basically, for those who don't know, when you shine light onto metal, there's a current that'll flow through it, and that's because the electrons in the light are giving their energy to the electrons in the metal, and they're producing a current. The third one was de Broglie's discovery of the wave-like behavior of particles. Has anyone heard of the double slit experiment? Okay, so for those, basically de Broglie put out that that particles don't always act just like particles. They actually have a wave nature, and he applied this to electrons in a theoretical paper, and then two scientists came behind him about 2 or 3 years later and experimentally confirmed his hypothesis. Okay? And the last one was Heisenberg's uncertainty principle. And if you don't know what it looks like, I actually have it tattooed on my arm right here, if you want to see it later. Heisenberg's principle goes thus. If you know the position of a particle, you can never know its velocity or its direction or its speed or anything. You can only know the position. And if you know the velocity or the speed, you can never know exactly where it is. Okay? And to illustrate this, so I'm a big footy fan. This is Bastian Schweinsteiger, Germany, Bayern Munich. In classical soccer, think about it this way. If you're a keeper, a goalie, and you're watching him, what 2 things do you need to know if you're preparing for him to kick that ball at you? You need to know where the ball is and how fast and what direction it's coming at you, right? And in classical physics or classical soccer, this is great. You can do this. In quantum soccer, right? In quantum soccer, if I'm the keeper, if I want to know exactly where that ball is, I can know that completely 100%, but I will never know which direction it's going to go in. Right. Or I can know exactly the velocity and the direction that ball is coming at me from, but I can never know exactly the position of the ball. Okay, so hopefully that kind of gives you a headcanon. A couple other concepts, because these will help when we get to the computers. We have entanglement. Entanglement refers to the behavior of when you have particles that interact. They can, I guess, a good way may be to imprint on each other. And so, using my particles again, if you have the blue and the pink, when they interact, they're automatically going to take an opposite spin to each other, right? So when they separate and go wherever they go in the universe, if anything affects this ball or the particle over here to make it spin differently, this one instantaneously will flip its spin so that they're always opposites, okay? And it may not seem pretty stunning if you're thinking like in the same room or at a different table, but they've actually been able to confirm this happens like across continents and even in space. And it happens instantaneously, which again, in one room may not be a big deal, but when you look at some of the distances this has happened at, the communication, I'm using that word real loosely now, appears to break the speed of light boundaries, okay? And Albert Einstein actually called this spooky action at a distance. He hated this. He absolutely abhorred this thought. He couldn't argue it didn't happen, but he just didn't like it. And if you're familiar with his quote, "God does not play dice with the universe," that's where he came up with that quote for this. And actually, I think another physicist, I can't remember which one it was, rebutted him. It might have been Hawking, but I could be wrong. He said, God does play dice with the universe, and sometimes he throws them where you can't see them. So I think we have a working vocabulary now to get into the quantum computers versus the classical computers. Is everyone here familiar with the Turing machine? Yay! Okay, so the Turing machine basically is a visual, conceptual representation of how data is processed through a classical computer, okay? And each piece that goes through is your bit, right? Your bit of information, okay? In quantum computers, instead of calling a piece of information a bit, we call it, we're very clever in physics, a qubit, right? And this is what a qubit looks like, and I know it's true because I found it on Wikipedia. It's an artist's representation of a qubit. This is going to take us to superposition, Schrodinger's cat. Most people are probably familiar with this, but just to go back over it again, in 1935, Erwin Schrodinger, a famous physicist in the quantum field, put together a thought experiment. This was not really done. No cats were harmed. Don't call PETA. Okay? But he was trying to illustrate this superposition concept. So the thought experiment goes as this. You have a cat in a steel chamber. Okay? In the steel chamber is a radioactive substance along with a device holding hydrocyanic acid. Now, if any of this substance decays, it trips some sort of hammer, it breaks the vial, releases the gas, and it kills the cat. Okay? So Schrodinger said as long as the box is closed, the cat exists in a state of superposition, meaning it's both alive and dead at the same time. Okay? It's not until we open the box, we observe the cat, we collapse the wave function, that the cat becomes either dead or alive. With me so far? This is real important. This is like the big one. Okay, yes. Okay, this is, for some they might see on the bottom, the Copenhagen interpretation. There's actually, if you're interested later and you want to go Google like I do, there's, I think at last count, 15 major interpretations of quantum physics. So this is that particular school. Schrodinger and Heisenberg were actually members of that school. But there's a couple others like the many worlds where there's theory and supposedly quantum evidence to show that there's not just our universe, there's like a bunch of different universes, but they're all together in one multiverse. So you may have, like, in another universe, my butt's not as big as it is now, or, you know, I have 4 legs or something. So there's the multiverse theory, and then there's a branching universe theory where supposedly every time a decision is made, the universe branches into 2 different ones with 2 different results and consequences. It's pretty fascinating if you're interested and you can't sleep at night. So superposition is important because this is how quantum computers get their stuff done faster, which is going to come critically and handy when we want to start breaking encryption, okay? So if you look at this qubit, it exists in a state of superposition, okay? When in a classical computer, your bit can be a 1 or a 0, the qubit can be a 1 and a 0 at the same time, okay? This may be a better picture, okay? So, parallelism. So in your classical computers with parallelism, you basically have several processors that are linked together and they can all do kind of different stuff at the same time. Well, in quantum computing, a single quantum processor can basically, if you picture that Turing machine, I can't find a picture of a quantum Turing machine yet, even though supposedly one exists in theory. On that strip of paper, instead of seeing a 0 or a 1, you can see a 0 and a 1 at the same time, and the computer processes both at the same time. And that is what speeds up your processing with the quantum computers. So far, we're good? Okay, and now this will be funny now because you'll understand it. So we have a little timeline just to kind of put some stuff in perspective with where the environment's been going. So in 1980, a Russian mathematician named Yuri Manin, he's the one who first proposed the idea of quantum computing, okay? And in 81, Richard Feynman, he's an American theoretical physicist, he proposed kind of a basic model for this quantum computer. Paul Benoff, another American physicist, he proposed the first kind of theoretical framework for that quantum computer. And then David Deutsch, he's with University of Oxford, he's the one that supposedly conceptualized the quantum Turing machine. Again, can't find a picture of it, but supposedly he's put that together. In 91, Arthur Eckert with Oxford also invented entanglement-based secure encryption. This is the neat one. In 2003, so this is more than 10 years ago, DARPA's quantum network became fully operational that year. So DARPA already has and has had a quantum network. In 2005, the first qubit is announced to have been created by scientists in Austria. And in 2007, a company called D-Wave Systems claimed to have the first working 28-bit quantum computer. A little bit about D-Wave. I've met one person who supposedly works with them. I will say I think D-Wave probably has some of the best OPSEC as far as security around what they do. Nobody knows what they do. Nobody actually knows if they actually do anything. That's how good they are. I have had about 50% of the people I talk to tell me that D-Wave is the genius tank. These are the people that are going to just, you know, revolutionize computing. And then I've had 50% of the people I talk to say they are all completely full of crap. They don't do anything. All their claims are BS. And since they don't really share anything they do, it's really hard to substantiate some of what they've done. So this is what they've supposedly done. I will leave it to you to decide if you believe it or not. In 2008, supposedly they had a 128 qubit computer chip. And then in 2009, supposedly Google started collaborating with them on image search technology using quantum computing. In 2013, we had coherent superposition of an ensemble of approximately 3 billion qubits for 39 minutes at room temperature. Now, this is a big deal because the previous record for that was 2 seconds. Okay? In 2014, scientists transferred data via quantum teleportation over a distance of 10 feet with 0% error. And in 2015, this was the week before I presented this at ShmooCon, there was an Ars Technica article that researchers created quantum memory that's stable for 6 hours in a very strong magnetic field at close to absolute zero. And then right before B-Sides Charm, I found this. This was actually kind of just really cool. So these guys in the Swiss Federal Institute of Technology have devised an experiment to photograph light as both a particle and a wave. And there it is. Ta-da. I thought that was really neat. So, why? Okay, so now this takes us all back to why did I start this in the first place? Like, so what does this have to do with cryptography, right? What's the deal? So, in 1994, a gentleman named Peter Shor with AT&T came up with an algorithm that would allow quantum computers to factor very large integers very quickly. Okay, and this algorithm can theoretically break a lot of the crypto systems in use today, basically most anything based on factoring or RSA. Okay, and the numbers I have are it can factor a 1,000-digit number in about 20 minutes. A classical computer would take about 10 million billion years to do that. And this is because of that ability to do this superposition and to the parallel processing of the quantum computer. So, a little bit on quantum cryptography. This was actually, I think all this is fascinating, or I wouldn't be talking about it. Quantum cryptography basically uses physics instead of math to encrypt your data. Okay? Well, no, you're actually using straight, I'm going to go into how it's done. You actually are using physics, not math. So you can't use math to break this. Pretty cool. Okay. So we all know Alice and Bob, right? So how do we do this? So we create a key using photons. So polarized light, get my particles again. So polarized light and unpolarized light. When light's unpolarized, it can basically oscillate in any direction, right? It's just all over the place, like my hair some days. When you polarize it, you'll pass it through a filter that kind of locks it into a specific spin. It could be diagonal, it could be up and down, it could be vertical, horizontal, whatever. But it kind of locks it into a spin state instead of it being all over the place, okay? So what they do is they use these filters and they create the photons using LEDs, and then they pass the photon through a filter, okay? And then the filter fixes it into a spin state, okay? So if you fix this one into a vertical spin state, the only way you can properly read this particle on the other end, on the receiving end, is if you have a vertical filter to read it through. If you place a horizontal filter, then that filter is going to change your spin state. Or it's just not going to pass through and it's going to give you a null reading. You're not going to get anything. Okay? So the way we do this is, Alice is going to transfer some random bits using random polarizations. Okay? So she's going to take her filters and set them up randomly, and then she's going to pick some numbers, and she's going to send them through. Just everything's random, okay? On the other end, Bob has no clue, you know? So he's just going to set his filters up and sit back and see what happens. He's just going to pick some, okay? Now, Alice can call Bob and give him her list of polarizations, not the bits she sent, just the polarizations. And then Bob can sit down and say, okay, we use the same polarization here, so I know that the bit that came through here is, this one is correct, right? Didn't get changed. And so what they do is the union of their two sets, that becomes your key. We good? Got it? All right. It took me weeks to get this figured out straight, and lots of whiteboard time with my developers. They were so good. So what about Eve then? Well, Eve can't do a traditional man-in-the-middle attack because any attempt to measure or to observe or to anything to affect that communication is going to skew what happened. And Bob and Alice, when they talk, are going to realize something skewed it, and they can scrap it, not use it, and go about, you know, picking another time or another place, or trying to generate another key where she might not be able to get in. The two known attacks for this kind of thing, because again, remember, you're using LEDs and you're using the filters. So you can't, you know, it's not like traditional cracking stuff where you can just do that. Excuse me. So the one thing I've found so far, unless there's something I don't know or haven't seen, is this all has to be done over like fiber optic lines. So it's not in the Wi-Fi stage yet. So the one attack would be just a denial of service type attack, where you just clip the line and they can't talk. The other one would be, instead of going after the apparatus that creates the photons and that does the filters, you would go after the random number generator that sets them. So you kind of get in front of it that way and maybe go after her random number generator. So this kind of takes us into the quantum hacking, which, like I said, it's been about 10 years since they've been doing this. And Planck Institute in Germany. So this gentleman named Nitin Jain, not sure I pronounced his name right, they figured out that Eve could take a laser and she could bounce it off Alice's filters, and she could get a reading of everything on the other end, right, without interfering with communication. So they said, okay, so they figured out they could put something in place called an isolator, which wouldn't allow any of her light to come in, or it would notify Alice if light was coming in on the other end, so she could, you know, scrap the effort and know that someone was trying to interfere. But what was interesting was, because, you know, I think physicists are just as much hackers as some of the rest of us, they thought, you know, let's test this, because at the wavelengths we typically use for telecommunications, the isolator worked fabulously. You know, they were able to detect that laser coming in. But if Eve were to drop down the bandwidth or go up a little bit, she was able to completely get past it, and no one knew. So then they have some other things that they thought about putting in place, some active listening devices that could detect that type of incoming light. So if you combined that with the isolator, then that kind of pretty much froze Eve out. But again, this was all 10 years ago. I haven't found a lot of recent research that's been published that I've been able to get through that's gone into anything else that's happened in the field since then. But there's your quantum hacking. So with the quantum computers, the big issue has to do around the factoring and how easy RSA and basically any type of cryptography that's based on factoring is to break using Shor's algorithm. Okay, so this has prompted this huge new field, which I actually wasn't aware about the first time I gave this talk, and then someone asked me during the talk, well, what about AES? And I had absolutely no idea. So I promised to go find out, and that kind of opened this door into post-quantum cryptography, which, you know, at the time I knew nothing about. They're looking at a lot of alternatives to factoring. So one of the things is lattices. Are you familiar with lattice mathematics? So there's a lot of really good YouTube videos, because I've watched almost every single one of them to try and understand it. Lattice problems are typically really hard. They're basically when you can have, this is like a two-dimensional, it tried to make it look three-dimensional representation, but basically it's a set of points, okay? And there's a set of problems that you have to figure out when you're dealing with a lattice environment, and they're like shortest vector problem. There are no known algorithms to solve these. It's incredibly hard mathematics, and there's no quick, efficient way to do this kind of mathematics. At first, I thought lattice sounded like it was being like, this is the answer, everyone start using this, but the more I've read, it looks like it's still in the stage where it's so difficult that using it efficiently from a cryptographic perspective in communications, not quite sure they're ready for that yet. I think it's still very theoretical. Another thing they're talking about is elliptical curve cryptography. Elliptical curve, anyone familiar with that? Anyone? Okay, so with RSA or with factoring, basically you have numbers and you're looking for the prime and you're just kind of trying to narrow it down. With elliptical curve, which if I actually get to talk at Black Hat and DEF CON, I will have slides on this and I'll be able to explain it better because I'll have figured it out better. You have a curve, and instead of trying to find a range of numbers like factoring, you're actually trying to find all the points along a specific part of this curve that have to do with an intersection. And they're not quite sure mathematically in even elliptical curve cryptography. It's being used for some stuff. I think like BlackBerry used some sort of implementation of it, but it's still really, they're working on it. And the other thing with elliptical curve, I'm actually reading a book on post-quantum cryptography where there's people arguing about the polynomial base of elliptical curve makes it just as vulnerable as factoring, but I'm still like 32 pages into the book, so hopefully I'll have that done by the next time I present something and I can share more, because I just started diving into this in the last month or two when I was asked that question. But the big advantages, again, with the lattice cryptography that they're saying now is over the elliptical curve, it's definitely a lot harder. And they're a lot closer to finding more efficient algorithms with the elliptical curve because it's been around a lot longer and it's been kind of attacked and played with a lot longer than the lattice has. So that's really why they're pushing lattice big. But again, only 32 pages in. I'll have more data next time I talk, probably. So where does that leave us? The big things that I took away from all my research are I understand better now why traditional cryptography, RSA, factoring type stuff is going to be incredibly vulnerable, because this algorithm is basically going to, it's going to be like, there's an app for that. Boom, you're done. There are people really trying hard to come up with an alternative to that type of cryptography, but there are still a lot of incredibly brilliant people who really aren't too sure about it. I think anyone who's studied cryptography knows that there's so much testing and attacking, and it's not just you can kind of pull it out of your pocket and have a new crypto system the next day. There's really a lot of stringent stuff that it goes through before a lot of people will agree that it's going to be effective and safe to use. And it's just not, I don't think anything has gone that far down the path yet to really be considered a replacement for the factoring in a quantum thing. And the reason, the only big reason right now that the lattice and the elliptical and everything else is considered, you know, secure is because essentially it would take a classical computer and a quantum computer the same amount of time to break it. So if anyone pops up tomorrow or next week and goes, whoop, got an algorithm, we're right back to where we are right now with the factoring. Okay, so it's almost like a crypto arms race if you think about it. There's also a big challenge creating the technology because of the magnetic fields and the extremely low temperatures required. You know, as I said, you know, 39 minutes at room temperature, that's not going to work for day to day. It's not, you're not going to be carrying this stuff around your pocket anytime soon. We're still really far from really having this as kind of a viable in your kitchen, on your desktop technology anytime really soon. But there are a lot of like really smart people and really rich people and countries and organizations that are probably a little further along than we know as far as like common knowledge. But it's not something I think is like really on the horizon yet. I think the last thing I read about viability was the current quantum computer that D-Wave claims to have can solve a Sudoku puzzle. That's about where it's at. So you can kind of extrapolate from there. And that's my talk. So hopefully you found that interesting and learned something. And does anyone have any questions or comments or smart remarks?
You're basically looking at how systems are moving away from what we know today. As far as being a laptop or a computer, going to a different substance.
Very much so. It's just looking at the fact that you're using physics to encrypt something versus math, you know, and then the hardware and the infrastructure type of requirements to actually have this in any sort of viable networking type environment or like super deployed type environment are still pretty. Now there's some real interesting stuff that they've put out there with cloud computing where they've talked about using the cloud environment for processing, because if you can put it there and it's not observed or measured, then you can put it in an environment where it can calculate in a superposition state because it's not being observed, and then once it's done, the environment will send it back with your answers. But I'm still struggling with it. There's a lot of math in these papers. There's like, you know, one sentence and then 3 pages of math and then a paragraph. So I'm kind of struggling through a lot of this as I make my way. Yes, sir. Are you stretching? Define near future. Oh, no. 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 Now, I actually had someone come up to me at SHMU after I talked who did some stuff with D-Wave. And I was like, can you get me in? Can I get a tour? I was like, ah! I, offered to do some probably inappropriate things for that. But we just don't know what, this stuff's really guarded. I mean, if I'm a superpower and I have the ability to do this now, I have the ability, it's like kind of having the Enigma machine, You don't want everyone to know you have it, because then they can try to mitigate that, even if it's just using a sneaker net or a typewriter. Yeah. I don't think it's theoretically impossible. I think right now the big issues, again, are the magnetic fields and the cold, the environment. But they've already got it, like I said, 39 minutes at room temperature. I'm sure they probably thought the phone I have in my pocket was pretty impossible 100 years ago. So, but 20 years, I'd say no. But in our lifetime, gosh, I'm hoping. Oh. I'm working out, so I'm getting a little more than 20, I think. There's a lot of interesting stuff out there that if you start reading, they've talked about using cups of coffee as quantum environments. It's pretty neat stuff, and there's a lot of really brilliant people out there working on it. So I'm really excited. It's coming, probably not that fast, but I'm not would. Oh, yeah, that would be cool. Set photon on stun. So any other questions? Does anyone want particles? I have a whole bag. Yes. See? Ooh. Boing. Trajectory, right? That was not a good trajectory. I'm going to walk back and hand those out.
No, just whiz one back and get
Okay. I'll just bounce it off his head, right? How do I do this? Thank you.